Today we're going to be looking at the relationship between arcs and the chords that form those arcs. So we're going to be looking at some theorems, so relationships that we assume to be true that we can then use to help us solve problems. The first one says that in a circle or between two congruent circles, if we know that the minor arcs are congruent, we know their corresponding chords are congruent. And if you notice the words if and only if, that means we can actually also use this relationship in reverse. If we know that corresponding chords are congruent, we can say that the arc created by those chords are also congruent. So in the diagram we have here, if we were to label these chords A, B, C, and D, because they tell us that chord AB is congruent to CD, and that's by the number of tick marks, right? They have one tick mark, which means those have the same length. Then we know that the corresponding chord, which would be A to B and C to D, would also be congruent. They would have the same measure. So the way that we can use that in problems would be to say things like if AB is equal to 5x, so that algebraic expression is representing the chord, and CD is equal to 3x plus 6, they want us to find AB and CD. So the first thing that we should note there is that they tell us that AB is 127 and CD is 127. It's in degrees, so that tells me it's an arc measure. And the chords are creating those arcs. So AB is creating the 127, CD is creating the 127 at the bottom of that circle. So again, if the arcs are congruent, they're both 127, that means the chords that make them also have to be congruent. If they're congruent, we can take and set the algebraic expressions equal to each other, and then we would solve for x. But the question says to find AB and CD, which means that we're finding the length. So we would have to take one of those expressions, plug in the number for the variable, and then solve. And because those two things are the same, they're both going to be 15. We could have also plugged in 3 times 3 is 9, 9 plus 6 is 15. We would have gotten the same answer using either expression. In number 2, again, we want to look for some congruencies with the arcs. So we have this arc measured at 80 and this arc measured at 80. So if those arcs are congruent and have the same measure, that means that the chords that create them also have to be congruent. Once I have congruencies, I can set those algebraic expressions and numbers equal to each other, and then solve for x. And that's what they asked us to solve for in this problem. So we're finished. You do want to be very careful when you're reading the questions and make sure that you're answering what they're asking, in that do they want the length or the measure of something, or do they just want you to solve for the variable. Our next theorem says that if we have a diameter or a radius that is perpendicular to a chord, then it bisects the chord and its arc. So this segment would be broken into 2 equal pieces, and then we would also have arcs. So it's breaking that arc into 2 congruent arcs. Again, you have to be told that it's perpendicular or shown that it's a 90-degree angle to be able to use the relationship that it's bisecting. In number 3, given that chord BC is 15 centimeters from the center of the circle, so that's our distance away, so that would be AD. The circle has a radius of 25, so anything from the center point to the outside edge is going to have a length of 25. Also, AE is a radius, so that one would have a length of 25. They want us to find the chord length BC and DE. So the first thing that we want to note is that AE is a radius. It's perpendicular to the chord BC, which should tell me that these two pieces are going to be congruent. So then the next question is, well, how could I solve for that side or one of those pieces? And we have a right triangle that is created with that perpendicular relationship for ADB. So we can use Pythagorean theorem to set up and solve for the missing side. So x squared plus 15 squared is equal to 25 squared. So 25 squared is 625. So to solve this problem, we're actually going to have to subtract 25 squared and 15 squared. So that's going to be 400. We would take the square root of 400, which is 20. And again, 20 is representing segment BD. So this is 20, which means that D to C also has to be 20. So that would mean that BC, so the whole chord, and again, this is where we have to be careful, they want the whole length, so the whole answer would be 40. DE is this little piece here. They tell us that AE has a length of 25 because it's a radius. So to find DE, we would take the length of the whole segment, which is 25, subtract the piece that we know, AD, and that last little part from the chord to the edge of the circle is going to be 10. So don't overthink some of those. Sometimes it's straightforward. Again, it's just putting the puzzle together. For number 4, we have to remember our 30, 60, 90 triangle rules. The reason I know this is a 30, 60, 90 special right triangle is because I have a 60 degree and a 90, which means this has to be 30. So they ask us to find AD and CD and the measure of arc AB. So for the first part, I'm going to use my right triangle rule, which says for a 30, 60, 90, we have a short leg, we have a long leg, and we have a hypotenuse. So it might have been a little while since you've looked at this, but we take the length of the short leg and we multiply it by radical 3 to get to the longer leg, which is across from 60, and the hypotenuse is 2 times the length of the short leg. So if the hypotenuse is 6, the short leg across from the 30 has to be 3. The longer leg is going to be 3 radical 3. Which means that D to B also has to be 3 radical 3 because these two are congruent based on our theorem. So now we know that A to D is 3 radical 3, and we know that DB is 3 radical 3. And CD, we found that one, so that one's 3. So 3 radical 3, 3. They want us to find the measure of the arc. So remember that the measure of the arc comes from the central angle. So we have 2 congruent sides because we have 2 congruent triangles. So this would also be 60 degrees. So the whole angle is 120, which means the arc also has to be 120. Our next theorem says that in a circle or 2 congruent circles, if the two chords are congruent if they are equidistant. So we would need to know that the measure from the center to the point where we touch the chord is the same. And again, they tell us that with a tick mark. The reason I know it's a distance is because we have a 90-degree angle, and distance is always measured at a perpendicular angle. So an example would be that in circle A, segment FG is 3, G to A is 5, and A to H is 4. And they want us to find the chord length for PJ and LA. So we have some right triangles that we have created with these chords because we have 90 degrees. So again, they have to tell us it's 90. 3, 4, 5 is a Pythagorean triple. You could set up and solve if you don't know your Pythagorean triple, but 3, 4, 5 is kind of the easiest one to remember. So now they tell us that these two chords have to be congruent because they're the same distance away. So once I know the sides of that are the same, and again, this is a radius, so it has to be 5. So we have congruencies here. So if I can figure out the measure of one, I can figure out the measure of another. Well, we have a chord that is being intersected by a radius. If we extended that segment out, we would have a radius at a 90-degree angle, which means each of these is bisected. So we're still using that other theorem that we talked about in our previous examples. Because it's bisected, now I know the length is 8. And this one would also have to be 8. So P to J and A to L would both be a total length of 8. Number 6, in circle A, FG is equal to 3x minus 4, so the entire chord, and H to J is 14. They tell us that these two segments are 2. They're perpendicular, so they're the same distance away. That means that the chord lengths must be congruent based on our theorem. So we can set 3x minus 4 equal to 14. Solve for 18, and x is equal to 6.